It's great to see you all. I am so glad to see that there are so many more people here today than there. I mean, we already had an amazing audience last year at the last OMSF workshop, and it was so fruitful. And some of the stuff I'll show here is a direct result of what we talked about last year. And it's been an amazing experience, and I'm so glad that I'm so excited to be giving the keynote for OpenFE this year. And I hope I can get you as excited as I am about this project, because it's my life, it's everything, and I just love it. I had a slide here because I realized David had briefly introduced open force, the idea of force fields, and because we spent 3 days talking about our chemistry, it didn't come to mind to even discuss what we were doing because I just thought everyone knew our chemistry. Open free energy does our chemistry. What does that mean? It means that we're interested in looking at how things change from one state to another. And primarily for the folks, I'm not going to go into the details, but for the folks that weren't there for the wonderful chemistry conference, we're really looking to improve predictions of binding affinity and any sort of state change. And that's really what we're looking for. Now, I've been in the field of alchemistry. I've realized I've been around for 10 years this month. Started my PhD, did a year not doing alchemy, and in 2014 started getting involved with the field. And I realized for a lot of you here, that means I'm still very much starting, because it's, some folks have been here for like 20, 30 years, and yeah. But what I've learned about this, and what I keep hearing at conferences, is that we still have a long way to go. Alchemy is really worked out. Like we have really amazing tools to help us measure differences in free energy between states. And they've been super. There's just a lot for us to do still. So these are a collection of quotes that I've heard over the Alchemistry Conference, mostly this year, but also 2019, because I think a lot of this was incepted in 2019. We have amazing tools in the community, but our biggest issue is the ability to have access to these tools. Effectively, the way I look at it is we have some islands with all these amazing tools, be they, the GrowMax, PMX tooling, or OpenMM tools enabling both RBFEs and ABFEs and so on. And it's really hard for a newcomer or someone that isn't necessarily used to a given tool to access it. And that is what Open Free Energy is about. We want to enable folks to be able to use tools for whatever endpoint they want. And we want to make it easy to use them in production, and we want to make sure that they're robust and well-tested. That's our main goal. We want to ensure that we have, we promote a framework for accessing all the wonderful tools that everyone is developing, and making sure that it's easy to use and that they're well-maintained, and that we really value what's been going on. And what we're doing is really we're bridging the application delivery and maintenance gap. And we want to make sure that we don't have any further duplication of efforts, that if best practices are being developed, that you know immediately. And that's really, that's the crux of OpenFE. Okay, and so we talk about OpenFE as I sort of give you a brief overview of the idea of OpenFE, but really OpenFE is its people. And we're here at the OMSF workshop, and really the thing that I want to spend my most time talking about are the people working on OpenFE, because more or less everyone in this room has in some way, either directly or indirectly, been involved with our development. And this could be that you were involved in the paper at some point that was really influential about the way we think. And I want to really celebrate you all and all the amazing work you've been doing. The core of OpenFE, in its simplest form, is its project staff. So these are the folks that are paid on a day-to-day basis to work for OpenFE. So this is all of us. Some of us are here. So we have Ben over there, and Hannah over there. And we are the folks that, a lot of the work that you'll see that I'll show today is being developed by us. Also to mention, we have 2 American developers, so David Swenson and maybe Josh is somewhere here? I'm sorry. Yeah, so I immensely appreciate these folks. They've done some amazing work and really have helped us get to where we are today. So we have a staff. We also have industry partners. So our industry partners are key to our survival. So the Open Free Energy is funded and led by a pre-consensus consortia of industrial partners. So we have 17 partners who give us money, which is important to hire our project staff, but also very tightly advise and collaborate with us on how they see the vision for OpenFE. And without their help, we wouldn't be able to get where we are. You know, we have constant meetings about them testing our tools and telling us what's working, what's not working, and really trying to get things into production. And it's been immensely valuable. So thank you very much to all of them. We also have an executive committee, and the executive committee is a subset of the board that has come together over the last couple of months, and they've been wonderful. They have addressed our need for better direction and better focus on our task. And I really want to thank Kira, Kaushik, and Joan Vitas, who are in the room, about all their work they've done. And I know they're extremely busy people, but they've been just wonderful at really getting our team together and getting things done. We also have a wonderful TAC. So this is our Technical Advisory Committee, which is led by several academic partners across the world who are helping us by advising on difficult alchemical questions. You know, we have several wonderful conversations with Stefan Barash about how we deal with dummy atoms. And it's something that hopefully will lead on to major improvements about how we deal with relative binding free energies. And these have been very useful. So aside from beyond that, we also have some really amazing project collaborations. And I really want to spend some time here to talk about David Dodson, who you'll hear about this a lot. But David Dodson and Ian have worked on AlchemyScale. And AlchemyScale has allowed us to test OpenFE at a massive scale, one that would be hard to do without paying lots of money. We have been able to get over 500,000 GPU hours of OpenFE testing, which is the only way in which we can be sure that OpenFE can be used in production, because otherwise this wouldn't have been possible. And the AlchemyScale team, whilst not directly in our project staff, have been tightly involved with the development and design of OpenFE. And they've been amazing contributors. And without them, none of this would be possible. We also have the ASAP team, who we collaborate with closely, and they've taken the OpenFE tooling, and you'll hear more about this later, but they've created this wonderful, thank you. They've created this wonderful extended framework around Open3D tooling, where they can now do open source drug discovery. And using OpenFE internals, they can do a full cycle and really design new compounds on go. And I didn't think at the start this would be possible. I thought, no way our tooling would enable this. Somehow it does. And that's just bewildering. And they've been tightly involved in sort of giving us user feedback, contributing new features, and just making things go forward for us. Then we also have collaborations on TAP members, and particularly a key one for us has been the Codera Lab, and led by John. And without them, we wouldn't be where we are. So a lot of what we're doing is based on so our MVP protocol for free energies OpenFE is based on the Perses framework. And without all their work, we wouldn't be able to do what we do. And so thank you so much to all of them. And I really want to highlight Irfan, who couldn't make it this year, but has been leading the development of OpenFE protocols outside of the core OpenFE infrastructure team. And so he has this FE flow package that I'll briefly talk about later, but it's amazing. It's going to hopefully enable external contributors to use the OpenFE tooling to develop the methods that they need. Another collaboration that has been wonderful is working with David Mobley and particularly Megan Osato. So Megan has been working with us for the last year, and as I'll show later, she's been involved in various benchmarking and validation of efforts, and she's taken on this very, I think, really interesting, but possibly quite challenging task of trying to dig down the sort of partial charge issues and the sort of weird and wonderful things you can get if you really push things. And she's also been a great alchemic scale test users. Then we also have the work that we do with the other projects within the OMSF consortia. So you've heard from Open Force Field just before. We have this really fruitful collaboration where we can sort of directly work together on joint tasks. So we've had some great help from Open Force Field in dealing with infrastructure issues. So if something breaks in OpenMM Force Fields, I can have a call with Jeff and get it fixed. And that's amazing. And I really want to highlight him, Matt, who has really gone above and beyond, and not only has helped us get our infrastructure moving to using interchange, but also is directly interfacing with OpenFE, opening up pull requests, and fixing things for us. And that's amazing. And then more recently, and you'll hear from David Swenson later, his OMSF infrastructure team. So David was in our team before and moved over to OMSF infrastructure. And with him and Ethan's help, we'll hopefully be able to expand our testing suite and run Fringy calculations directly in testing suites. And that will allow us to be even more sure about the quality of the software that we release. And then if we're talking about OMSF, we have to talk about the OMSF staff. So I also want to celebrate the folks that helped OpenFE exist. So without David and Carmen, OpenFE just wouldn't be here. They helped incept the project. They helped set up a lot of the base of the legal framework and everything for how OpenFE works. And they've helped it stay alive for the last 2.5 years, and we're very thankful. The person I really want to highlight here is Zach. Zach, who is all over there, I'm immensely thankful for Zach. So not only has he really, he brought us all here together. He set up this event and has been doing amazing work within OMSF, but he's also come to OpenFE and changed our work culture. And that's something I didn't think he would even have time for, but somehow he does. And Zach has changed our development structures, has made us more agile, and we're now able to get even more done with the same amount of time. And I just don't know how you do it, Zach. And then finally, we have a community. And we're a brand new project. Well, 2.5 years. So we're newish. And we don't expect to have a large community. We expect it'll be friends and family. It turns out people are using us, which is surprising to me. Shouldn't be, we're great. Pardon me. So on our key metrics, since last year, we've essentially tripled download rates and things like that. Now, there's a caveat that, so these are Conda stats, the download numbers of how often people are downloading OpenFreeNG. There's a caveat that this could be based on people just using us more on SCI suites, but it means people are using us more on SCI suites. So we're getting used more, and that's great. And we've heard throughout the last 3 days that there are a variety of folks that are using or testing OpenFE internally within in industry. And pointing to Hendrik's wonderful talk, but also there's folks that we weren't even aware were using it that are. And that really speaks to this sort of, the fact that this is working and people want to adopt it. So I've covered the people, which is really the main crux of my talk, but now I'm going to talk about what we do. We have developed an entire ecosystem for doing FreeNG calculations, and what I'm going to do is cover some of the newest things that we've been working on. So first is our infrastructure. So Open3NG really sits on top of a key piece of code called Goofy. This is a common workflow language based on a series of abstract classes that allow us to define the main building blocks for expressing 3NG calculations. And the idea here is that once we define this, folks can then use this to create 3NG workflows in the ways they want. So OpenFE as a toolkit is an opinionated form of Goofy. And we're seeing use for Goofy outside of just what we do. For example, David Dodson, who is a core contributor for Goofy, uses Goofy within our Chemiscale, and technically can be used outside of our core tooling. And similarly, Irfan is using Goofy components to develop protocols that we don't maintain or develop. And throughout the last year, we've been expanding it and making it more stable. And what we're doing is effectively just making sure that we have a good common workflow language that can cover the domain of applicability of the variety of 3NG calculations we want to run. Now, one thing we showed last year that we've been working on or improving is our command line interface. So we have the OpenFE toolkit that allows us to run 3NG calculations. And what we've done is made it simple enough to run 3NG calculations in 3 lines of bash. You can plan, run, and analyze a simulation with what's on this page. So if you have a set of SDF files and a protein PDB, you can get to a set of 3NG results. And to me, that's bewildering. When I was doing my PhD, this would have taken me weeks to set up. And so the fact that we can do this so quickly is insane. And also, of course, you still have to wait for your simulation to run, but it makes life so much easier for us. And what we've mainly been doing is expanding our CLI to be able to handle more complex settings. So we have a variety of tooling that I'll speak about that allows us to define how we set up simulations. And we've been expanding our CLI to be able to give better user choices. For example, what type of network you want to create, and if you're using a radial network, what your central ligand is going to be, and things like that. And we're currently working to expand it to the point where it will arbitrarily pick up settings from different 3NG protocols. So then you can define, for example, how long your simulation is going to run. And look out for this, because it'll come out in a couple months. And the other thing we do is, so we have a framework for running simulations that's either we can run them through our Chemiscale or locally through just a serial execution of our 3NG protocols. But what David Swenson was doing before he left us was working on improving that. So he created this tool called Exorcist, which allows us to execute complex tasks in a seamless manner. And this will allow us to run very complex simulations and spread them over HPC facilities easily. And I can't wait for this to work. It's coming soon. All right, so that's infrastructure. Now, we've also spent a lot of time working on FE tooling, and this is some really amazing work. So atom mapping is a key problem in relative binding 3NG calculations. You need to be able to define how you move from one molecule to another. But it's also an incredibly difficult problem. When we started Open3NG, the gold standard that we had was the LOMAP package developed by the Mobley Lab. And it worked fine, but it had some issues. Because it relied on an MCS, or a maximum common substructure approach. And it meant that in certain cases, particularly when you dealt with stereochemistry, it was really hard to define the atom mapping. And that meant that as an application person, I had to sit down and manually validate a ton of mappings. And it made life difficult. And so what particularly Ben did is that they decided that, well, let's think about it in a different way. So we started looking at creating a new atom mapper called Cartograph, which is 3D first. So it avoids the idea or the difficulties of the NCS problem by just directly looking at the distance between two pre-aligned molecules. And there's a caveat, is they need to be pre-aligned. But it works wonderfully, and it is fast. You can scale up to whole proteins. It's very flexible because it allows you to define rules on mapping for how you want your mapping to be. So if you have an opinion about how your transformation should be, you can define them. You can say, for this series, I want to exclude this type of functional group transformation. And that works. And definitely significantly reduces the need for manual intervention, which is a big plus. And we've tested this on a variety of systems, so we apply this to protein ligand benchmark because we want to make sure that the mappings provided were of adequate quality. And compared against the low map gold standard, we're getting statistically similar results. I think 90% of all our mappings are the same, but compared to low map results, I didn't have to look at them ahead of time. The other thing that we're working on in the setup space is, well, we've got atom mapping, so we can define how we do a transformation from one state to another. But we also have to define how we do a network of transformations. How do you plan a simulation? Because now, at the end of the day, you want to look at how one molecule transferred not just to one, but like to 1 million other molecules. And so you have to create these large transformation networks. And so what we've been working on is this connector package that Ben presented actually on Monday. And the idea of connector is to quickly and easily create large and complex perturbation networks. The package offers a variety of different ways to handle these networks and analyze them. And what's really cool is you can do really fun things like if you have a series of compounds and you want to cluster them. So let's say you have a net charge transformation and you want to avoid doing lots of net charge transformations because they're very expensive. What you can do is use connector, for these 2Ks, to cluster your compounds and create subnetworks. So you have a series of compounds, we've clustered them, and now we're able to create 2 subgraphs that we can connect later on. And then now we have lots of transformation within the same charge and very few transformations with different charges. And that will significantly improve the simulation or the performance of our simulations. Because we don't have to do twice the amount of work because we're doing net charge transformations everywhere. So that's a very brief review of what we're doing with setup tooling. We're working on lots of different other tools, but these are the ones that are production ready now. And please try them out. We're also working on a variety of fringy protocols. So these are different ways in which we run simulations. Our current MVP, and this is something we showed last year, is a Perses-based protocol, which allows us to do hybrid topology fringy calculations. So we are able to do relative hydration binding fringes. We have a variety of samplers that are available for MPM tools, so we can do HREX, SAMs, and independent sampling, and it's something that we've been working on and manual editing. So what we spent a lot of this year is increasing the domain applicability. And we're confident at this point that for the majority of soluble protein cases, barring metallic proteases, this works. You can use it in production. Now, there are a variety of non-soluble protein cases, some membrane proteins, and that's next year stuff. But for now, we're confident that this works. So one of the things that we've been doing to expand the domain applicability, and what we weren't able to do last year, is to handle net charge transformations. So following on some work that Ivy had done for Perses, what we've done is implemented the ability to deal with net charge transformations by preventing the artifacts caused by one state or another having a net charge. So what we do is we use our chemical waters. So we try and take one water in one state, transform it to an ion in the other, and we make sure that we have the same charge or neutral charge across all our windows. And this has been working really well. The only issue is it obviously needs longer simulation time. But when we compare it against, for example, what Schrödinger's been doing, we're finding that on our validation benchmarks, we're getting, if not the same, or better results. So these are very few edges, but these are part of Schrodinger's charge change validation benchmarks. And aside from CDK2, we're doing as well. And that really allows us to be confident that this is working. CDK2 is a challenging system, and we're trying to work out what's going on here, but yeah, aside from that, it works. Now, in terms of protocols, so I mentioned we have different samplers. So what Irfan's doing is actually building a new protocol that extends the sampler for this hybrid topology method. So Irfan has been developing FE-flow, and he's been working on a non-incremental switching method that was already available in Perseus before, and just making it available within the OpenFE framework. And these are new results from Irfan on this, and comparing the two methods, we're getting very similar results, mostly within error. These are very short simulations, so we've got a few outliers, but it's working great. And we're looking forward to be able to use this. This will be really useful when deploying on things like folding at home. Now, we're also working on new protocols, and it's something I've been promising for a while, but we will get there. We will get absolute binding for energies within a couple weeks to month, mainly validation left. And so we are working on getting absolute binding for energies in, and we'll have a stable release soon. And we have absolute hydration for energies already, and we're using that internally for protocol validation. We're also, hopefully by the end of the year, looking to extend into other protocols. So we want to, Hannah, who worked a lot on setup, will hopefully be implementing separate topologies in OpenFE, and then we'll be working with VTAS on getting a GROMACS protocol in. Because the important bit about OpenFE is that we are not meant to be opinionated about the frameworks or the methods we're using, but be able to enable them all. And enabling different MD engines will be a first step in moving out of the OpenMM ecosystem and looking at other things. And we want to eventually be to a point where we can support multiple engines with different protocols. So we're really looking forward to doing this, so we can bring that promise of open for energy is for the entirety of all the different islands of all the different methods. Now, one thing that we've been doing on the protocols that actually came out of this workshop last year is we heard a lot of folks in the industry saying, hey, it's really hard for us to understand what's going on in our simulations. So we took that to heart and we addressed it. So now we have automated analysis reporting on our simulations. So at the end of every simulation, we create a set of output files that will tell you exactly what happened. So we have, for example, all your standard energetic analyses. We also have a variety of structural analyses. So, protein RMSD, how close your ligand was to its initial person binding pose. And we're also adding things like dihedral analyses. And it's something we want to keep working on, and we definitely need feedback on. We need to know what type of analyses you want so we can implement them. And then hopefully we'll get to a point where you can even just custom create your own analyses. And that's hopefully coming within the next year or so. So that's a very brief tour of what we've been doing internally. The very big thing that we've been working on is validation. So we want to get to a point where we are stable. And so with the help of particularly Alchemy Scale, we've been continually running benchmarks in Open Free Energy. And we are at the point where we're, on the PLB, we're at a point where we're getting results that are very similar to what other folks are getting. And one thing to mention is we're close to a new release of the PLB, so look out for that. And hopefully, this is a lot of work that John's lab has been doing, and hopefully we'll have a new stable version of protein ligand benchmark systems. But yeah, we've done a lot of work in benchmarking, and things are looking great. Now, we do benchmarking of OpenFE internals, but we also have been helping out benchmarking of other tools. So when new force fields are getting released, we've, in particularly work that we've been doing with Megan, is we've been trying to help out validate them, because now that we have OpenFE tooling, we can quickly swap out different force fields or test out different components. And so that's what we've been doing, and so we've been helping out with validation of the open force field releases for the last 2 releases. And talking about Megan, sometimes benchmarking doesn't go well. And Megan has been helping us with that. So something that Lily was mentioned earlier was that sometimes what we found out in some of our benchmarks is sometimes we were getting extremely large error bars. And this was particularly, this came a little bit to a surprise to us because originally we were using the OEChem backend and we switched over to just using Amber tools. And then we started getting these massive errors. And it turns out that Amber tools on different computers will get you different partial charges. And these are very tiny differences up to 0.07, but they lead to giant error bars. And this is particularly true when you're doing a cycle and the two legs of your cycle are being assigned different partial charges. So now you have giant differences. Now, a quick, easy way of remediating them is just to use the same conformer. You just generate your charges ahead of time and you fix that. So that's our current approach. Well, what Megan's doing is actually looking, I didn't have a slide. What Megan's doing is looking into this more and trying to work out what the limits of the partial charge generation issue is. You know, are there ways in which we can fix, for example, Amber tools and get that done? And I'm really looking forward to her work. And please have a chat with her. She's done some really amazing work. Something that Lily also covered is that there are ways around this. We can use, for example, Naggle. So one of the things that OpenFE does is it allows us to swap out components easily, as I mentioned earlier. And so what we can do now is we can directly use Naggle in our fringy calculations. Just say, okay, use Naggle instead of Antichamber or OEChem, and we're able to quickly benchmark things and see how well they're doing. And as Lizzie mentioned, from our initial benchmarks, Naggle is performing amazingly well, and we're really excited about its use. And that's a very sort of quick look at what we've been doing. But with all this validation on all these new tools, we're now at the point where we think we're stable. We have an API that works. We have benchmark results that seem to indicate that for the tests, the domain applicability that we want to be reaching, we can do calculations and we can do them well. So we just recently released our first release. And we're now, at least for these systems, we think we're now production ready. So we're looking forward to getting this into your hands and seeing how well it behaves. And that's really what we're doing now, is we're now moving on to a phase of industry benchmarking. And we are doing a two-phase benchmarking study with our industry partners, where we will do a series of evaluations on public data sets and internal private data sets. And hopefully by the end of the year, we'll have a publication ready where we'll be able to say, hey, this is how well OpenFE does on all these data sets, and then you'll be able to confidently move forward being like, this works, this should work in my production setting. And so recapping our timeline, so we started in 2022. We initially focused on getting OpenM MRBFEs in. We worked on cost graph, particularly last year, and getting all our setup tooling done. And now we've reached a stable release. And finally, we're now moving to doing some industry benchmarking. And later in the year, we'll be looking at getting advanced methods in. So ABFE, scaffold hoping, and other MD engines. And beyond this year, we haven't really worked out a roadmap yet. So this is something we want to hear about from you here, but also we'll be reaching out in the latter half of this year. And so please use this as a way of fostering ideas for what you want to ask, because we need to know what you want. What we think we need is really to start expanding on domain of applicability. So we want to start looking at membrane proteins. We want to be able to deal with more challenging cases. We know that waters are a problem. You may have hard conformational transitions. So we may want to look at GCMC or REST2. There's also lots of wonderful methods being developed at the moment. Ladybugs, reads, time-square sampling, and ATOM. And so these are all different avenues we can go to, and we're really excited about what we can do next. And finally, I just want to thank you all. This wouldn't have been possible with all of OpenFE's contributors, and both direct, indirect, and upstream. And we look forward to continuing to work with you. And please try out OpenFE. We're really confident about the 1.0 release, and we think it'll do great.